Hello, chemistry learners. This is Jennifer Brazier, and welcome to Equilibrium. Now, in chemistry, we're used to reactions that seem to go only in one direction. For example, when we burn wax, the wax reacts with oxygen to make carbon dioxide and water. We don't imagine that the carbon dioxide and water are going to hit each other and remake the wax. That seems to be one direction only. However, in other reactions, they might be easily reversible. For example, we have this reaction here where dinitrogen tetroxide decomposes to form two nitrogen dioxide molecules. But those two nitrogen dioxide molecules may in fact hit each other and reform the N2O4. This is a reversible reaction. Now, these double arrows that you see, it means so much more than just this reaction can be reversed. In fact, this double arrow right here means that this reaction, if left to its own devices, will eventually reach a state of equilibrium. Now, in everyday language, equilibrium is the state of balance. But that word balance can get chemistry learners in trouble. In fact, it can be a huge misconception. What we do not mean by equilibrium is that we achieve balanced amounts. That's not true. Equilibrium is not balanced amounts on each side. Instead, it's something else entirely. So let's examine this chemical system in order to try to figure out what it is. So we have dinitrogen tetroxide that can decompose into two NO2s. We're going to start this reaction by having only N2O4 in some container. So our original amount of N2O4, let's place that up here on a concentration versus time graph. We're going to start the reaction with only N2O4 and no nitrogen dioxide. So concentration-wise, the nitrogen dioxide, I will label that right here, starts at 0. Now, as the reaction proceeds, we're going to start to use up our reactants. So the concentration of the dinitrogen tetroxide is going to start to decrease. We're going to start to build up the nitrogen dioxide molecules. That concentration will start to increase here. Now, as our amounts begin to change, something interesting happens to the rates of those reactions. Remember, we know how to write rate laws based on the stoichiometry of this reaction. So we could look at the rate in the forward direction for N2O4 decomposing. The rate in the forward direction, I'll call that rate F, equals the rate constant Kf times the concentration of the N2O4 to the first power. Now, at the beginning of this reaction, we have a lot of N2O4, a high concentration. We're all reactants. So we have a high initial rate for the N2O4. But as we start to use this reactant up, as the concentration of that N2O4 goes down, so does the rate. How quickly we can go ahead and change N2O4 into NO2 will decrease. So the rate, I'll label this K in the forward direction times the concentration of N2O4 starts to decrease. Now let's look at what's happening over here at the nitrogen dioxide. We can also write a rate law based on two NO2s reacting and going in the reverse direction, producing N2O4. The rate in the reverse direction, I'll call it rate R reverse, equals the rate constant K reverse times the concentration of our NO2 squared because we have a coefficient of 2. Now remember, originally we had no concentration of NO2. We're starting with no product. So if this is zero concentration, the rate in the reverse direction is also 0 here. But as we start to convert reactants to products, we build our concentration of NO2. That means the rate in the reverse direction will start to increase as well. I'm going to label that K reverse times NO2 squared. So the N2O4 begins to dwindle. The NO2 starts to rise. The rate of our N2O4 continues to decrease. The rate of the NO2 as we get more and more and more of this begins to increase. This one decreases, this one increases until we achieve the same rate. So our rate reverse will increase till it reaches some value. The rate in the forward direction decreases until it reaches some value. Once the rates are equal, we have reached equilibrium. So at this point right here, equilibrium has been established. The rates are equal. So when we were saying balanced, it's not balanced amounts, it's rates being equal. Now what about the amounts? Okay, so the concentration of my reactants, N2O4, will continue to decrease until we're trading back and forth equal amounts until the rates are equal. At that point, the concentration should be steady right here for my reactant. When I'm trading back and forth, the amount that goes this way equals the amount that goes this way, the concentration won't change. Same thing goes with the reverse. The reverse amount is going to grow and grow and grow and grow and grow until equilibrium is established and we're trading back and forth equal amounts, and then the amounts of my reactants will not change. So at this point, equilibrium was established. So equilibrium is established when rates are equal or concentrations do not change. So your concentrations are constant. Okay, so those are the big keys. Rates are equal. Concentrations are constant. Now, some people think your reaction stops at this point. That's not true at all either. This is not static equilibrium. Instead, we are just trading back and forth equal amounts. So it seems like the piles on each side do not change anymore. It seems like your reaction is unchanging, but things are still happening. It's just there's no overall change in amounts. So equilibrium, equal rates, constant amounts. I hope that helps.